In this video, I'm going to go over vectors, matrices, and tensors. So in general, I'm going to try and make this course have as little mathematics as possible, but in some areas it's really unavoidable. And it's really, really important that you have a sound structure of these three objects if you're going to do deep learning. In particular, you really need to understand vectors and what we're doing with vectors. Matrices and tensors become more important when you're looking at computer vision tasks and you're working with images, but they are still important because you will be using multi-dimensional data when you do deep learning, just by the fact that you're going to have, if you have like 100 examples of one thing, then that will be 100 vectors, which itself will become a matrix. So it's really important to have a solid understanding of these things. That's what I'm going to go through in this lecture, and I'm going to try and keep it as straightforward as possible. So we'll start off with vectors because they are the simplest. And a vector is very simply just a one-dimensional array. So by this, I mean it's essentially a set of numbers that have been grouped together to become one object. So it could literally just be 1, 2, 3, 4, and then we put these brackets around the outside to signify that this is a vector. And we're going to use these a lot because our outputs of every single neural network that we use is going to be a vector, almost always. So one of the ways that you can think of this is if we have two dimensions, if we have two features, x1 and x2, and let's say we've done some normalization to get them between all between 0 and 1. And we've got 2 points that we want to consider. So the first point is A. That's going to be at 0.5, 0.5. So if this is point A, then we very simply have A equals this vector 0.5, 0.5. So this, if you haven't seen vectors and matrices before, this sort of idea should be something similar to what you've seen, but maybe not in this exact representation. So if we have a second point, let's say B, and this is at 0.2, 0.8, it's exactly the same thing. Okay, and in general, we can define any point by this vector x1, x2. So we can represent any point on this square, this 1 by 1 square, by this vector x1, x2. So reasonably straightforward. One of the nice things that we can do with vectors is try to work out the distance between these vectors. And there are a few different ways that we can do that. What this allows us to do is work out how similar two vectors are. So you've got the L1 distance, the Euclidean distance, and cosine distance as a few examples. So if these are features that you've already looked at, maybe one of these is like to do with age, maybe it's to do with height somehow, I'm not sure. It doesn't really matter that much. Whatever these features are, we can always do some of these very nice distances. The most simple one of these is the L1 distance, where we just do, again, if this is now A and this one is B, we just do x1 from A take away x1 from b, and find the modulus. So if we do, in this case it would be just 1 minus 0, and then we have this modulus function. I'm going to give that like that so you can see it. And then we add the modulus of 2 minus 2, the modulus of 0 minus 2, and then modulus of 3 minus 4. I know a lot of you haven't come from a maths background, so if you don't know what this modulus is, it just takes any negative number and it'll make that positive. So in this case, for the L1 distance, we're just going to have 1, 0, 2, and 1, and then we add that up, and that's the distance between our matrices. For the Euclidean distance, instead of having this modulus, we're instead interested in the square. So again, the square is going to make everything go from negative to positive. So it'll look like that. And then we'll just take the square root. Kind of probably the most useful, at least in recent times, because of things like BERT and GPT. We see a lot of people now that are using a mechanism which is based entirely on the cosine distance. And the cosine distance says that, like we saw before, we have two vectors. So before we had these two vectors which are 0.5, 0.5, and then the second one was 0.2, 0.8. What the cosine distance is saying is we want to find the distance, we want to consider the direction that these two vectors are pointing. So that's pointing in this 45-degree direction, and this one's pointing in a slightly more upright direction. And we want to find the angle between those and do the cosine of that angle. And the formula for that is we do cos theta is going to be the dot product of these two. So it's going to be A dot B over the modulus of A times the modulus of B. So this isn't really too important for now to go into like full depth of what this actually means, but I do want to explain the dot product because that's a very, very useful thing that we're going to be seeing over and over again in one form or another throughout these lectures and throughout deep learning in general. And the dot product, if we do A dot B, is going to be, instead of before where we were doing a subtraction of one of these to the next, we're instead just going to multiply them. So we do 1 times 0 plus 2 times, maybe I'll use a, yep, so 2 times 2 plus 0 times 2 plus 3 times 4. And that's how we find the dot product of two vectors. So this is going to be really important, particularly when we look at convolutional neural networks. So now a matrix is very, very similar to a vector, but instead of just having this one-dimensional form, we're going to have something more like a box. And we see that images are composed of matrices. So before, where we just had 1, 2, 3, 4, we now might have more than one row. So we go to something like this, where it'd be 5, 6, 7, 8, and these can be any kind of dimensionality. So, well, I've said it's in 2 dimensions, but there could be the size, the number of columns could be any number, and the number of rows could be any number. There's no restrictions in place on that size. And the place that you're going to see this the most is with images. So here is an image of the number 7 from the mnist dataset, which I think Matt has already shown you. And this is a matrix which is 28 width and 28 dimensions for height. So there's 28 columns, 28 rows. And for any image, the pixels that are black are going to appear as a 0, as we've got here. And then as they get more and more white, they're going to become closer to 255. So this is like here, this is 254. It's very, very white, almost as white as it could be. So it gets a very, very high value. And usually when we process these images, we squeeze all of this down into the range of 0, 1. But that's not too important for now. For now, we can just look at it in terms of the raw numbers. So there's some important operations that we need to know about matrices. The first one is a scalar multiplication, and this is very simple. If you have a scalar, which is just a regular number on its own, you simply multiply each value in this matrix by that scalar. So the 1 becomes a 2, the 2 becomes a 4, etc., etc. Shouldn't need to go too far into that. Then we've got the matrix transpose. So when you have this matrix M, if you want to transpose it, essentially we're doing a flip in this axis, in this diagonal. So the 2 and the 4 swap places, the 7 and the 3 swap places, the 8 and the 6 swap places. Again, it's not too important, but we should be, it's not too difficult, but it is very important. So we should be aware that this has some very nice properties that we will use if you ever study AI to a more advanced level, or maths to a more advanced level. This transpose is very, very helpful. And lastly, we have matrix multiplication. So I need to explain that we have 2 different types of matrix multiplication. The first is an element-wise multiplication, which isn't being shown here because it's very, very similar to the dot product we did before. So I think I'll go over it here just because I can. With an element-wise one, you just do 1 times 1, which would be the top left corner, and then the second. So you'd have, if we get rid of this for a second, you'd have 1 times 1 would be the top left corner, and then 2 times 4 would be the top middle, then 3 times 7 would be the top right, etc. So that's an element-wise multiplication. But you also have this matrix multiplication, which is slightly different. This is usually given a symbol like this, whereas element-wise multiplication so an element-wise is usually just this dot. So it's similar to the dot product. Right, so the matrix multiplication, what we do is we start off with this 1, with this top row and the first column. And we do this operation where we first start off by multiplying the 1 and the 1, and then we move across here. So we start off with the 1 times 1, and then we move across. So the next thing we've got is the 2, so that's this one, and then we've got this 2 as well, which is this one. So, and then finally we have the 3 by the 3. So we go down on the second matrix. And then we get 14, and it's where this row and this column intersect that gives us where this final answer that we get is going to be on our outputs multiplied matrix. So for the next one we do exactly the same thing. Because this highlighted row intersects with the highlighted column at this point, that's the place that we need to put in this calculation in the output matrix, and we do 1 times 4 plus 2 times 5 plus 3 times 6, which is what we've got here. That becomes 32, and we can do the same for the next row and column, and then we do the exact same thing but we move down a row. Okay, so the exact same thing is happening all the way through, and you'll see when we do this, because this is m, because this is m not squared but transposed, you see that this matrix is symmetric in this diagonal. So these two are the same, these two are the same, and the 50 and the 50 are the same. And this is just one of the nice properties, one of the nice things we can do with this transpose operation. So far we have looked at vectors and matrices. Now we're going to take a look at tensors, which is where we have multiple matrices stacked on top of one another. So before we looked at number 7, which was a grayscale image. So that image was represented as a single matrix. But when we're looking at color images, we can't actually get enough information from one image on its own. That means we need 3 different grayscale color images that represent different things. So we have one channel which is of red color values, one for green, and then one for blue. And you can see in the red channel we've got this very light colored pepper, which corresponds with the highly red pepper, and this is essentially all that's going on. So if something is highly red, then it should get a high value in this red color channel, and then when we actually observe this channel, because it's a single matrix, that makes it grayscale. So the whiter it is, the higher the red value. And you can see, for example, as well, that this like garlic and this onion, because they're composed of red, green, and blue, that they all appear fairly similar in each of these color channels. So this image, like I said before, is going to be composed of these 3 stacked channels, one for red, one for green, and one for blue. So in this case we've got a tensor. Well, it's not exactly 128 by 128. Let's imagine that this is height 128 and width 128. Then you're going to have a channel dimension which is 3. So now your image size is going to be 128 by 128 by 3. And just to note that once we go further, once we have more of these things, we're no longer going to have new terms to consider. Everything which is more than 3 dimensions or more is just going to be described a tensor. So if we've got a video which is 100 frames, and the image size of each of those frames is 128 by 128, and if it's a color video, then it's going to be 128 by 128 by 3 by 100, and this is still a tensor. Here, just to like clarify, this is what you'll see when you output the size of a tensor in PyTorch, but it might be easy to think of it as 128 by 128 by 3 by 100. Whatever works easiest for you.